In the previous lectures in the course, we have analyzed a few mechanisms by which one gets collective macroscopic dynamics only by assuming quite simple, so to speak, microscopic interactions between the elementary objects in that system. We'll continue with this effort of characterizing different mechanisms, and now we will concentrate on one mechanism which is very much characterizing the growth clusters in the economy. Nowadays, it was understood that the economy of country is growing not by having the entire country out of a sudden starting to produce more or to be more sophisticated in its products, but actually having very, very singular locations which become so to speak, Silicon Valleys, or in the case of Israel, as I mentioned, it was called Startup Nation. But in fact, it's even inside Israel, which is a small country, the place where this happens, it's a very small part of the territory. So we'll try to understand how this happened, why it's happened, and how we can get to a situation in which to encourage this kind of growth centers to appear and to encourage the wealth which is produced in those growth centers to diffuse within the entire economy. So when speaking about collective dynamics, the best example is to think in terms of atoms and our body. Each of the atoms doesn't do anything special, and even when it's inside our body, it does exactly, it fulfills exactly the same laws as in fact it obeys in a stone. However, collectively together, they do have a very non-trivial behavior, like we exemplify by our functioning, and this is the kind of generic thing which happens when one gets complex dynamics in terms of very simple microscopic interactions. So we are going to explain this to give at least a metaphor which would help us understand how you get this kind of jump between the microscopic behavior of the elementary components of system and the collective emergent objects which have completely different properties, such as adaptation and personality and wish to survive and things like that. And again, we are returning to a frame of mind which was formulated by Phil Anderson, in which he said more is different. How many elementary microscopic interactions, which are very simple, can lead to so very different and very complex behavior macroscopically when they are put together. And we are going to concentrate in this lecture to a system which is the simplest system which has this kind of properties. Now, it looks a little bit scary, does it? Because it looks like formulas, but it actually tries to say, it's not even a formula, it's trying to say the following, that the entire system, which I'm going to discuss now, is made out of two types of, let's call agents or particles or individuals, A and B. Now, the A's don't do anything. They just go around, diffuse around. Suppose that if they live on a kind of grid, then they can jump on the neighboring sites with a certain probability per unit time. However, they are important because they influence the behavior of the other agents, B. The B's also can jump from one place to another. But in addition to this, they can multiply. They can, however, multiply only if they have they are in the same place with an A. So this formula, so to speak. It only says that if you have in a certain place an A and a B, then another B can be generated with a certain probability per unit time lambda. And the bees, they can multiply, but they pay this by also being able to die. And they also compete. If there are too many bees on a place, then one of them might disappear. Is it clear? Now, even if it is not clear, in fact, I have an animation of it. Because it was suggested. So what does it mean, this system? You can imagine, in order to remember what the A's and the B's are doing, you can imagine that this is a space in which the A's and the B's live. And the A's can jump with a certain probability on one of the neighboring sides. Okay? And the B's can do the same. They can jump up, down, left, and right. And how do I represent? And as I said, when the A and the B are on the same side, they can produce another B. And if A and two B's are on the side, with each of them there is a probability that lambda per unit side that another B will appear.
What do you mean on the side?
On the same square. If one is here and one is here, there is no probability for another B to appear. But if they are on the same place, then another B can appear. And there is this probability for B to die. And also, as I said, if the B's are either on the same side, and sometimes even if they are on the neighboring sides, some given radius, they will compete, and one of them has a probability to disappear. So this is a system. Now, in order to make it intuitive, I endowed the A's and B's. I pictured them as humans. But in fact, they are not humans at all. They are not animated at all. The rules which I invented about them, they are very mechanical. They are a little bit like the rules for a molecule. If you have two molecules, there is some probability that if they are in the same place, they will interact. There is nothing that they can do about it. They cannot wish it. They cannot. They don't wish it. They are not against it, and they cannot change it. So why am I emphasizing it? Because you see, these very simple systems, a system of A and B's, which don't want anything, which cannot influence, which are not even influence. B's are not, for instance, attracted by the A's. They only multiply when there is an A in the same place. This system, I will show to you that it has properties which are very, very similar with the kind of organisms which are emergent out of the molecules and which do want to survive. They do make moves in order to preserve their own existence, and in fact they do succeed to survive. So the reason I'm teaching this model is exactly because it is the simplest model in which you have this kind of thing happening. You put very simple interactions, which are definitely not adaptation or wish to survive or intelligence to try to survive, and you get, in terms of the collective objects of B, which are going to appear spontaneously. They are going to appear themselves from these interactions, not by me doing anything in addition. Those objects will have the properties which are a metaphor, at least, for the kind of properties we have in terms of trying to survive and to improve our situation. Okay? Is it clear what is the objective? And is it clear that it's, in a sense, quite ambitious thing? We start with almost nothing, and I'm promising so much. You'll judge yourself to what extent this metaphor is satisfactory or not.
Do you mean physical survival?
I mean, yes. In fact, I do mean the following. I will explain in a while. even if I take the parameters of the death of the bees very high, and the parameter which is the reproduction of the bees, lambda, I will remember to you. Well, this is not mathematics, just Greek letters. If you want, we can change them to other letters. But the point is that you have a certain rate of birth and a certain rate of death for these bees. And I showed to you that in pictures, yes? Now, you might think that if the average rate of birth is less than the average rate of death over the entire system, the bees will die. Yes? If somebody tells you on the surface of Israel there would be a certain amount of certain probability for people to die and a certain probability for newborn to be born, then you would think that the growth of the decay of the entire population depends on whether the birth rate is higher than the death rate in average. This is not real. What I'm going to show is that this is not true in a system in which is not homogeneous. Because it might be that there are small places where there is a very small population and it gets even smaller and it has a high rate of death, but there are some other places which are very populated and they are getting even more populated. And therefore, even though when you make the average over the entire territory, you get a higher death rate than birth rate, then in fact, still the population might grow very significantly. At this level, you understood. Now, everything which I'm going to say for quite a while now, it's an elaboration of this mechanism such that we can estimate in great detail whether this happens or doesn't happen. And in addition to this, as I said, we'll get as an additional bonus the fact that those places which have this property that their growth rate is higher than the average, they start behaving like a unique object, like a collective object of all the people in that place, and behaving very in a way that it enhances very much their fitness, like Silicon Valley, like the region in the north of Tel Aviv where all these companies are interacting with one another and producing billions every few weeks. Sorry. Yes.
And explain it like with mortality rates.
Yes. You see, there is the probability, I call it dA because it's diffusion. It's the probability for an A to go around. You can imagine, for instance, that it's capital which is going on different places in a region. And no, in fact, you can say that it's about people with technology, people educated, people going. And this is capital, B. It also can go around, let's say on the surface on some territory.
Both A and B can do the same.
They can do the same thing with different rates. Maybe the B's go faster than the A's. These are parameters, okay? So I'm happy that you asked me, because you see, if you see a D index B, you might think that it's who knows what a complicated thing. It just says what is the speed of jumping of the bees around the different places.
So why isn't the little b capitalized?
Because it could be. It's a convention. You'll see. I'm differentiating between each individual B, which I use it as a capital, and the entire population, which I'm labeling by a small b. It doesn't really matter. I could have as well write index B. What is really important is, you see, if the A's and the B's are on different places, nothing happens. They just go around. And however, if they are on the same place, there is a probability that they will make another B. Now this probability is lambda. Now, forgive me, but I didn't realize that using a Greek name would make a difference. But all it says is that in the same way in which I'm telling you that they can go around faster or slower, I'm saying that they can, that if an A and B are on the same place, they can create another B faster or with less probability per unit time. Okay? And if there are more B's or more A's, then essentially the number of B's which can appear is proportional to the product of the number of A's and the number of, with the number of B's on that side. Each A and each B can make another B, okay? Remember that.
Can one A make another B?
This A and this, each of the two B's, now in place of having a probability lambda to have another B, there will be a probability per unit time 2 lambda. It will be faster because each of the B's can create another B together with the A.
What about the bottom line?
No, these are the new ones, which I'm just.
New ones also?
The new ones, yes. That's the point. This is a crucial point about this system. You see, the crucial point is that even if that in the moment that I have one A and one B on a side, then this kind of assumptions of saying, okay, the distribution of A's and of the B's over the entire territory is more or less uniform, so I'm going to use the average number of A's times times lambda as a measure of what is the growth rate of the B's, because I have so many A's on the territory, and I have this lambda. So the B's will grow with a rate which is proportional with how many A's I have.
You only need one A.
But if I have 2 A's, then I double my rate. That's the rule of the game.
But if you have one A, like what will make the system stop? It'll continue to go.
Yes.
Just at a slower rate.
At a slower rate. And here is the place to explain to you that I have also the death rate. You see? I have the death rate.
Could you explain that again?
Yes. If I have a B sitting there and not meeting any A, it's not just getting bored. It has a chance to die. It will die, I don't know, like people die because of an illness. It can die because they are old. Or in the case of, let's say, a capital which you invested, if it doesn't produce, it's being consumed. You have to pay for the building in which it is hosted. You have to pay for the salaries of the people, even if you don't produce anything. So just having a bee sitting there without producing, and even if it is producing, it's still each bee has a certain probability to die. Okay? So and this is mu. So now the probability to
Probability that a bee will die, or the probability that a bee will die if it doesn't meet an A?
the death of the bees have nothing to do with A's. The bee will die with the same probability if there is an A around or there isn't an A around. The question is whether before dying he is making another bee or not. Okay? The A's are only helping in making new bees, are not helping the bees, the existing bees, to survive. Okay? Because of this, the computation is very simple. I have a certain probability for bees to appear, which is lambda times A. And I have, because it's proportional with the number of A's which I have, and I have a probability to die, which is mu. Okay? That is all you have to remember. And there are, of course, this diffusion. So this allows me, these explanations which I just gave to you, allows me to jump very fast to transforming this system into a system which is very similar.
We need the table to my class.
This thing, this talk of mine, it's recorded and put on the YouTube. Please close the door.
Could you explain the third one again?
Say it again.
Could you explain the B
Yes.
plus, no, B plus B,
This one.
the third?
This one.
No.
This one I don't want to explain very much. I can explain. I'm saying the following. Suppose that there are two animals. Suppose the bees are animals, and they need to have a place to shelter themselves. Or if you want, a capital needs some place to be invested. If already somebody invested in that company, then this capital cannot be invested there. It might be lost. Or if an animal is looking for a shelter and that place is taken by another animal, it might be left out. Or if there is some food, and so when there are two competition, exactly. But this term I don't want to discuss it very much because it's not going to be crucial. The crucial thing is this competition between lambda times A, the rate of growth. Okay, because it's lambda, it's the rate for one A. But if I have more A's, the number of A's times lambda, this at that place, this is what decides how many new bees are being born. And there is mu, which says what is the fraction of bees which are dying in a certain time. So I had here a lot of explanations of which you can now ignore because I already gave you the explanations, and which I'm saying the following. Essentially, if I want to know in a certain place, suppose that on a certain square, I have a certain number of A's, okay, and a certain number of B's. Now, what is going to happen? It's going to happen that there are going to be lambda times A times B new bees to be born. Because each pair of, if I have 20 A's and 30 B's, then there will be lambda times 20 times 30 possibilities to build, to generate another B. So it's lambda times A times B. It's contributing to the new value of B. It's what I had before, 1 times B, it's what I had before. But at the next time, I will have what is born, lambda times m times b, minus how many they are dying, which is the probability to die, mu, times how many I have. So if I have 100 bees in a place, and I know that each time step 10% are dying, then I will have this 0, 1 times b. There will be less. 1/10 of the bees will appear in the next step. But I have these other ones. Now, is it clear until now?
You lost me.
Excuse me?
I'm lost here.
You are lost. I want to know, I suppose that I have a little a is the number of big A's on a square, okay? Suppose that there are 3 A's on a square, okay? And suppose that there are 2 bees on that square, okay? Now, suppose that the death rate of the bees is half. So,
That's always mu?
huh?
The death rate is
Yes.
always mu?
Mu. So mu is half. So the next time step, I will have the number of bees which I had initially, which is 1 times b, at time t, yes? Minus half which have died, and plus 3 times lambda times b, which are the new bees which are born. Okay? It's not clear why it's lambda times a? Suppose that each a and b can produce with probability 1/3, okay? 1/3 of a child per year, okay? And now there are 3 A's, okay? So each of the bees have 1/3 of a probability of a child from each of the A's. But there are 3 A's. So in total, the expected number of children of the bee from these A's which are here, it's 1. Okay? So in total, I would have 1 plus 1 minus half. I will have 1.5. B at t plus 1 will be 1.5 larger than b at time t. Okay?
And what are we putting as time t?
Excuse me?
What are we, in what the example you just gave, what was time t?
Time t is, suppose that now it's t, 26 of May 14. And now I'm asking how many bees will be 1 year from now. And if there were, let's say, as I said, there were 2 bees, and now I have 1.5 times 2, it's 3. I will have 3 bees next time. Okay? It's 1 plus, what did we say, plus 1, and minus half. So the point is that if lambda a minus mu is larger than 1, then the bee population will grow. If lambda a minus mu is less than 1, then the bee population at that time, at that site, will go down. Is it clear? Now the point is the following. You ask, what does it have to do with t? Why do I quote t time? Because what I want to do now is to say, okay, but this relation between assuming that a is constant, this relation between b at a time with b at a previous time, is true also at time t minus 1, at time t minus 2. So, because of this, if I'm asking, if I want to understand what is the evolution of the number of bees in time, each time that passes, each unit time, I will get multiplied my previous value by 1 plus lambda a minus mu. 1 plus the birth rate minus the death rate. Okay? Is it some? This is the birth rate, this is the death rate, and this is what I had before. But b of t, as I said, it's itself 1 plus lambda a minus mu b of t minus 1. So if I want to express b of t as previous and previous years, I can say that b of t is 1 plus lambda a minus mu b of t minus 1 times 1 plus lambda a minus mu squared of t minus 2, because I use the fact that in place of bt I can put 1 minus, and so on. I can go farther and farther back in time until I connect the value of the number of bees at time t with the number of bees which were initially. I had this, suppose at the beginning of the state, I had a certain number of bees, b0. This is time equals 0. And each year, I had what I had before, times plus what was born, minus what was dead. And each time I had this multiplication. Each year there was another factor like this. So if lambda a minus mu was larger than 1, then I would have that bt is increasing. And in fact it's increasing like this exponentially with t in the exponent.
I don't know where that t came.
Look here. If bt is, I express bt in terms of b of t minus 1, yes? And this is the expression. This I explained. Now, but b of t minus 1 can be expressed in terms of b of t minus 2 by saying that it's b of t minus 2 times 1 plus lambda a minus mu. And together with 1 plus lambda a minus mu before, it's 1 plus lambda a minus mu squared. So and now I can go ahead and say b of t minus 2 is 1 plus lambda a minus mu times b of t minus 3. Therefore, 1 plus lambda a minus 2 squared, and another one which is coming by expressing b of t minus 2 in terms of b minus 3 is 1 plus lambda a minus mu to the power 3. So I can go on until when? Until it's t minus t, which is 0. But so in terms of 4, I have here t. So it's b of 0, but it's 1 plus lambda a minus mu to the power t. So again, if 1 plus lambda a minus mu is larger than 1, then I have this increase. I have larger and larger values of b. It's an exponential increase. And if lambda a minus mu is less than 0, then I have an exponential decrease. This is so Now the real point, and of course if I also take into account this competition, which I didn't take into account, then there is a correction to it. At the beginning I have this kind of exponential going up or going down, but because of this competition, in place of this going to infinity, it will saturate. So basically what is...
Explain what the competition, is that the B plus...
The competition, it means that if the bees are too many, then it's not anymore true that they will grow indefinitely. It's like in this room. In the moment that it's full, suppose that people are coming, suppose that each time there is somebody sees somebody here will come, so it will be proportional, the number of people coming would be proportional with how many there are already. So you have this kind of exponential which I explained. But when it gets full, then it will not increase anymore. Okay? But I'm not going to, this part is not really very important. The important thing is to understand that this model, if I don't take into account the fact that, the system has many different places where the A's can fluctuate, and therefore the exponent can fluctuate, if I consider the entire system as one single unit, it will either go exponentially up or go exponentially down, depending on whether lambda A minus mu, whether lambda A, the birth rate, is larger or smaller than the death rate. Okay? So this is
You just said that if you do not take into account the system has various places where A's can fluctuate, and so exponents can fluctuate.
You see, I made this computation. This computation here is assuming that everybody is in the same box. I have A guys and B guys. But if I have more than one box, then some of them will have more A's and some of them will have less A's.
Okay, but we haven't spoken about how one box influences another.
First of all, we did implicitly. We said that the A's and the B's from one place, they can go to the other. This is only influence. You remember the D index A and D.
We didn't speak about how that can happen.
This happens. Just there is a certain probability that any A will jump on the neighbors and any B would jump on the neighbors. This is going to be taken into account. The point is that when people have written these equations very many years ago, I mean, this model in this format we kind of invented, postulated. But when you write in terms of differential equations, the differential equations, I mean, in terms of this kind of recursive equations, I always... this kind of thing, which we have done very much at the beginning of the course. It's my way of explaining to people which don't want to hear about differential equations, things which usually are expressed in terms of differential equations. So this kind of expressing the value of B at t plus 1 as a function of B of t, if I assume that A is constant, that I have one A in one place, one number of A's in one place, this is a formula and this is the result. And this is more or less what these people have done. And what we are going to do is to say, yes, but I have, in fact, more places, different values of different number of A's in different places, and on top of this, they are jumping from one place to another. Now we are going to take this into account, okay? For the moment, I didn't take it into account, and they didn't, because they say, you know what? They were, in fact, studying the population of the Netherlands. And they said, okay, the Netherlands is 1 square. And I have a certain number of Dutch people there, B of t. In the year 1679, I don't remember the exact date at which Malthus has done the statistics. And then he said, he went to the king, and this maybe will give you some motivation to take to look at this equation, because based on this, Based on this measurement of what was the population in some year, and based on what was the population in the next year and maybe the next year, he said, wait a minute, this thing here is positive. The population in the Netherlands in our times, the time in which is growing, and it's growing with this kind of factor. We are going to have an exponential increase of the population of Holland, and I can compute in how long it will take until the Dutch people will not be able to lie down because there will be not place in this country anymore. This is what he came and said. He wrote a book. It's very famous to this very day. Did you hear about Malthus before? Well, this is what he said. Maybe what I'm going to teach from this second on during this lecture might be less interesting. But what I spoke now, it's guaranteed very interesting. It's an idea which has a career of 300 years and didn't finish to this very moment. Actually, it was only now which maybe these bad prophecies of Malthus are going to be really dangerous. Until now, it didn't happen. Maybe it will not happen even now. But now people are really very seriously worried that the number of people on this earth is more than, let's say, the number of places where we can put our waste.
And he spoke specifically about the Netherlands?
He had the data from the Netherlands, yes. It's difficult to call it Netherlands because at that time Netherlands and Belgium were not really separated. But he went to the king and he told him, look, it's going to be bad. And this is however, the point which I'm making here is that it's actually from the opposite direction. Even if this term is negative in average, even the total, if the total number of A is such that lambda A is less than mu, if you don't take the entire Netherlands as one box and you look at different boxes, you will see that some of the boxes, indeed, most of the boxes are going down, but some of the boxes are going up. And the ones which are going up, if they continue to go up, then they will fill the entire system. So this is the main effect which I want to speak about, okay? Yes?
What do you mean by negative? That what's negative?
Just a second. Lambda A minus mu. This is the growth, the birth rate, and this is the death rate. Huh?
Of bees.
Yes. And this can be negative if the birth rate is larger than, it's smaller than the growth rate. In average, then you might think that the entire population will go down. And I'm saying be careful because there might be situations in which it looks like it's going down, but there are regions which they are small now, but they are going to grow and they are going to be the main.
Because those regions are growing at a
I don't want to explain too much of this because I will have in a few minutes, if I go on, I will have very clear quantitative examples of economy of after liberalization of communist countries. You will see this kind of effect which I'm speaking about with the eyes. I don't have to speak about it abstractly. These ones, as you see, they are written in gray because I knew that I don't have to explain too many. You don't have to concentrate on this. The main point is this. Essentially, it's a way which is not in terms of differential equation, but it transmits in a way that we already got familiar with. It transmits the idea of Malthus, that the population of time t gives an expectation for the population of time t plus 1 in terms of the birth rate and the death rate. Yes?
Why are we using that kind of model if, with this angels and mortals if we're going to talk? talk about Malthusian dynamics. Why are we using that kind of model?
What do you mean by angels and mortals?
If we're going to talk about Malthusian dynamics. I mean, in reality, it's not that way. I mean, A's do die off, and B's don't have to fight each other. And
first of all, the B's are fighting one another all the time. The fact that the A's don't die is because I want to have these simple equations. If I make the A's also die, then the equations will be even more complicated. I will have to write an equation for the A.
I know maybe they'll be more complicated, but maybe they'll be completely different.
Yeah, that's true, but I'm going to get there. Meantime, I wanted to give the example which transmits this very concept of having a population of bees which is submitted to a certain growth rate and death rate, and which, if I take it at the global level, then I come up with certain predictions, and if I go to the microscopic level, you'll see that I get completely different conclusions and predictions, which are completely confirmed by the experimental empirical data.
Okay, and does this model, because I know in the analysis model, there's a state of saturation.
Yes.
So this thing also doesn't look like it goes to any level of...
No, but there is this saturation which is due to this B squared. I mean, look, I have to, in these lectures, I have to keep a balance between giving the main idea and not getting into secondary ideas which are as difficult in terms of the mathematics, but they are much less important. I want to even the level of mathematics which I have now, apparently it's making some problems. So I want to concentrate on the things which I really cannot avoid. And the thing which I cannot really avoid is this kind of exponential increase in the B's. Okay? In as far as the A's are going, you can think about resources, let's say like sun or water, which are virtually not consumable. So I wanted to tell you that in this 200 years between, so it wasn't 1600, it was 1700 that Malthus invented it. In this 200 years which passed, this kind of logistic, it's called the logistic equation, when you add also the competition term, has been very, it's called the logistic equation. If you ask me why is it called the logistic, I don't know, and what is a logistic equation? The logistic equation is the equation, it's this equation, in which you have this term, but also the B squared term, the competition term. You might also have...
So we don't have to understand.
What?
Didn't you just say that we don't have to understand?
No. Did you understand this?
As much as I'm going.
Well, I'm happy with that. I will go for that. Okay. So, now, let me give you another reason for which I am writing this thing. Does this thing remind you of something?
That thing that I didn't understand before.
It was when it was W here, it was our old equations, which we discussed in great detail. And this is, if I don't take into account the nonlinear term, the B squared term, this is written more generally, but this is the B squared term, and this is the diffusion term, the things which you asked me about. So I don't want to discuss them, at least not more than I need. But this one, you definitely do remember that we had this kind of situation in which the entire system was not in terms of one single B, but there were some different subpopulations, if you want, or individuals which were indexed by the index I and were independently, or rather not so much independently, because they were coupled by some conditions, they were undergoing this kind of multiplicative process. Multiplicative, in fact, random process. Why is it random? Because the coefficient A, which I took it constant, actually A If I take many different places, the age is not constant. The total number of age is constant because they don't die and then they are not created. But on each different site, because the age are jumping all the time, they are random. So we are back to a system which we have studied during this course, and about which we know many things. We know, for instance, that the distribution of the B's, of the values of the B's, fulfills a power law, which for the moment is not that important. It will become important in maybe in this lecture or maybe later. So, again, we have this equation, which you can write it as if in the entire system is in one single box. And this equation has been around for 200 years, and people were extremely happy about it. They felt that it captures the main things which makes life special: reproduction, and death, and competition, and traveling. So sometimes when I'm teaching it, I'm saying, well, there are all the ingredients for a very good Hollywood movie. You have love, you have crime because of the competition, you have death, and you have travel. But seriously speaking, these are indeed, things are important because they have this kind of autocatalytic property. What does it mean, autocatalytic? A quantity whose change is proportional to itself. This is, at least in the view in which I'm, the dominant view of the present course. It's the claim that the source of getting macroscopic dynamics, macroscopic collective objects, macroscopic complex phenomena out of simple microscopic things is this fact that the quantities are reinforcing themselves. If something is if the population in some place or the wealth in some place is big, then its growth will be bigger. And if in some place it's low, the growth will be smaller, or maybe even negative. And this, as I said, was actually said by those people, but not in the level of many little squares, at the level the big squares. So the problem now is that, okay, these equations are very nice, but essentially, as long as we are speaking about one single box, the prediction is that either you fill the entire box with, because of the exponential increase, you fill it until it's saturated, until it's felt, or if it goes down exponentially, if lambda a minus mu is less than 0, then you are left with nothing there.
Before you said 1, now you changed it to 0.
Because there was a 1. There was 1 plus lambda a minus mu was larger than 1. No? You don't believe me?
No, I just don't.
Good. This is, you see, now you start having a scientific attitude. Don't believe anything. Here it is. 1 plus this was larger than this. 1 plus this was less than 1. And then
Like
this.
That means time 1? The 1.
What do you mean?
What is the 1?
The 1 is what I had before. 1, it says, what I had before, plus what was born, minus what was dead, is what I have now. Now, do I have more than what I had before? 1. Or do I have less than what I had before? This is the only thing which matters in order to decide whether you have a decreasing exponential or an increasing exponential. And then if this is larger than 1, then obviously this is larger than 0, and this is, if it's less than 1, this is less than 0. Understood? Good. So if lambda a minus mu is larger than 1, or another...
If 1 is what we had before, if there's no 1, what does that mean?
If 1 plus this is larger than 1, it means that what I had before plus what was born minus what was dead is larger than what I had before. Therefore, I have each time more and more population. if 1 plus this is less than 1, which means that this itself is less than 0, then each time the number of born minus the number of death would be negative, and I will have all the time less and less, until I will have nothing left. Understood?
I just don't understand why before I had a 1, and you said that 1 is what I had before. You mean in that specific example, the number 1 is I had 1 before?
You have a certain population at the time, at last year, okay? 1,000. Now, 30 were born and 20 were died, okay? How many will you have now? 1,010, okay? 110, yes? So, if it would have been opposite, that 20 were born and 30 were died, then you would have 90. Well, would be 100 minus 10. So this is the 10. This could be plus 10 or minus 10. It's what is in addition to what you had before. What you have next year is what you had before, plus what was born minus what was dead. So what was born minus what was dead, if it is larger than 1, then you have, it's larger than 0, you have more population, and if not, you have less population. The fact that this is less than 0, it means that 1 plus this is less than 1. Nothing else.
So you got rid of the 1 because
1 appeared in both places, therefore I can erase. Yes?
so before we also could have erased it. It just, to me, it looks like you changed the equation. That's why I'm trying to figure out why before it said less than
Yes,
1.
this equation, when you put 1 plus 1 here and plus 1 here, it's equivalent. These are equivalent. Okay? Remember this. This is terribly important, and it's something which
I'm sure it's very obvious to you, but it's not, clearly not.
if one number is larger than the other, then 1 plus the first number is larger than 1 plus the second number. Is this mathematics understood? Good. So this is what I did. So the point is the following. As I said, now I moved the old guy on the other side exactly for what I said. So you have the new value minus the old value. It's essentially equal with A, which are the conditions at a different place, times lambda minus mu. Except that now I'm saying, wait a minute, but the conditions are not really identical in every place. This is going to make a lot of difference, because you see, now this is a map of the A's. And in some places you have a red point because there are 2 A's, and in some places there are no A's, the blue, and in some places there is 1 A. So the conditions are not uniform, and you might say, okay, but I still can take the average. That's the point which I'm trying to make in this lecture. Taking the average is not allowed in this, because in the places where you have more A's, you would have an increasing exponential, while in the places where you have no A's at all, you will have essentially only deaths, and you will have a decreasing exponential. So the point is that the number of bees at a certain time would be, as I said, would be proportional with 1 plus how many A's I have in that place. This is in place of a little a, because I want to emphasize that it's number of A's in that particular place. At the power t with time, and with the probability of having this kind of number of A's. So what happens, even if you don't, so knowing that it's not good to write a formula, I'm writing it now in terms of words. What I'm saying is the following. That if I have that the dynamic of the system, this is an A's, the distribution of the A's. It's pretty uniform. This is just zoomed in. The distribution of the B's given this distribution of the A's is going to be very different. This one, it's not completely uniform because it's discrete. You have an A or you don't have an A. But roughly speaking, it's the entire territory is filled with a uniform distribution, statistically uniform distribution of the A's. The result of this on the B's is very different. Why? because there are some places, some small places, where there are many A's. Those places are very rare events. And they are very small. But this is where the B's are growing very fast. So this is an explanation of something which is nowadays very much described in the behavior of many systems in economics and in in society. It's called very rare extreme events. Instead of relying on the fact that you know what is the average behavior of a system, it starts being true that what is really governing the behavior of systems in society and in economics and in many other, in ecology, for instance, too, is very rare extreme events. So here we have these islands of B, which are very large. This is a logarithmic scale, so these red things are orders of magnitude larger than the rest of the thing. And the parameters were chosen in such a way that if the A's would be really smeared completely uniformly on this side, then here you will have 0. Then here you will be in the exponential decay regime. But as you have it, you have most of the system, which is indeed unpopulated with bees, but there are these islands of bees which are existing there, and their behavior is very, very interesting. Not only that you have this non-trivial and unexpected emergence of the bee island, but the bee islands will behave as if they are intelligent and if they want to live. Because what will happen is that if there is some excess of A's which is producing this island, and now the A's are going away, then the bees themselves, the individual bee will not go after the A because he doesn't know. It's not what we put in the model. But what happens is that the bees which don't go in that direction will die, and the bees which go in that direction will proliferate. So the island will follow the fluctuations in A. The islands behave as if they want to live, and if they are intelligent enough to understand that they have to go in the places where the A's are existing. This is another simulation of it. And this is another simulation which is very simple because it has only very few A's. So you see how the islands of the bees are following the A's. And again, this is when I first gave a talk about this, I said, you see the bees are following the A's. It is not true. The individual bees are not following anybody. It is only the collective system, the emergent objects, which are complex enough to be able to follow the motion of the A's. And here is another simulation from the side. And you see something very interesting here. You see that the height is fluctuating. Why is it fluctuating? Because when A goes to the other point, all the bees which were at the previous point, they are going down. So we have very large fluctuations in the system. Not only we have an explanation of why do you have survival, why the stock market is flourishing in spite of the fact that so many companies are going bankrupt. Especially, it takes the example of Silicon Valley, 99% of the companies are going bankrupt. But there are these singular ones which are making enough money to compensate for the rest of the system. This is another simulation, again with parameters in which the naive system, if you take lambda, the value of lambda, the probability for a single pair of A and B to give birth to another B, and if you take the density of A's and you multiply them, this would be the naive average growth rate, and it's taken to be smaller than the birth rate. And still, as you see, the system does something completely else. That is the kind of paradox, if you want, on which this life, at least in this metaphor, is basing its very existence. And very many of the properties which we are witnessing in reality, and which I'm going to describe in more detail. So not only we give an explanation of the emergence of, so to speak, living systems, but you'll see that from now on, and probably beyond this lecture, in the next lecture too, I will have an entire series of very precise predictions which this model does and which are exactly fulfilled by the empirical data. Sorry. How do I get out of this? So in particular, we had this model. I come from a rather theoretical field, string theory and things like that. So we were happy with theoretical models, which were full of these paradoxes. But at some stage, we had a friend which had the data about the Polish economy immediately after liberalization. And for some while, we were, me and especially my students, we were looking at that data, and we couldn't really make sense out of them. So I said, wait a minute, why don't we look at whether we have a situation in which most of the economy is going down, but already from the beginning there are very small places which until some moment they are not even visible, but which are eventually growing exponentially and taking the lead of the economy. And in fact, this is what we found. So this is the kind of typical situation we have, that you have parameters lambda, a, and mu, which would say that the system has to go down exponentially, but in fact, it not only doesn't go, at the beginning it does, because the entire system goes down except the singular growth points, and then it starts fluctuating because even these growth points, which were initially the growth points, they are moving themselves. And then when it's moving, the place where they were is going down, but the new place is going up. So you have fluctuations. So this is the kind of dynamics I'm going to describe, in which you have these locations where the number of A's is very large. They are very small areas. They are very rare. So therefore, at the beginning, they are irrelevant when you start the system or when they appear. But they are very fastly growing. And because of this, they are eventually influencing. So you have this kind of situation in which, because of that, you, instead of an exponential going down or an exponential going up, you have fluctuating, you have first of all the exponential going down, but then the recovery, and then a lot of fluctuations which are related with, which are much larger than the fluctuations that you would expect from the B's, because the B's are so many, and the square root of the B's is much smaller than B, but the fluctuations are not coming from the fluctuations of the individual B's. They are coming from the appearance and disappearance of entire islands, and because of this, the fluctuations in the system are macroscopic, like we see them in the real economy, in the real society. Our societies are not stable, and having just square root of root Gaussian fluctuations. We are having very massive fluctuations, very massive changes. So. This is the program which this kind of thinking is putting in front of us, and which is a very vast program. I will show to you in this lecture and the next one just the tip of the iceberg in terms of what are the kind of quantitative predictions and quantitative policy suggestions which this kind of system can give. Excuse me? Now I'm saying it in words, so maybe the point is the following. Because these systems are made out of discrete elements, they cannot be completely uniform. You see, water can be completely flat, at least at the scale at which we are looking of it. But, or if you have some butter, you can uniformly spread it on a piece of bread. But if you have caviar, you either have a little bubble there or you don't. So once you have this discreteness of the underlying individuals which are forming a system, like people, like companies, like products, then you have microscopic noise. Now, because of this situation in which the variation, the new value of the beads is proportional to the old value times a number, you have this exponentiation, and because of this, this microscopic noise is amplified to macroscopic values, which leads to the appearance of macroscopic objects. Now, these objects are not obliged to look like the microscopic objects which they are made of. And this is where we very often are coming and saying to people which are still attached to the representative agents in economics, in which they assume, okay, so I look how an individual behaves, and I give what they call microeconomic fundament to the macroeconomics. How? By assuming that the entire community of individuals behaves like the individual itself. And here we find that this is exactly the opposite of what happens. The collective macroscopic objects which are obtained, which are emergent spontaneously, without me doing anything, that out of the virtue of the dynamics of the system itself, they have emergence properties, which are the main one being adaptability. And moreover, we find that this also means that the system at the macroscopic level, in place of being just some kind of average with very small fluctuations, which are in percentage going down with the number of participants, in fact, this is not happened because the fluctuations are not related with each of the individuals, let's say each of the B individuals dying or being born, but with entire islands of B appearing or disappearing. And this gives us, in fact, predictions which are similar with what we already computed, because you remember, in the moment that I have the individual fluctuations macroscopic, then I can relate, like we did in the first part of the course, I can relate the distribution of wealth, let's say, of different companies or different individuals at a given time with the kind of fluctuations I have in time for the entire system. So I can relate the social inequality to the stability of the system. I can relate the growth rate of the system with this kind of inequality which exists, because this tells me how fast the fast growing parts of the system are growing compared with the rest of the system, which maybe is not even growing. But this doesn't mean that when I make the sum of all of them, I don't get a lot of growth. So even if only very singular regions in the system are growing, they are growing so fast that in fact they cause the entire system to grow, as in fact this recurring example of the Silicon Valley is coming to my mind. So here there is a rather interesting being in a humanistic campus here. I would make this digression about a philosophical digression in which you see that the emergence of the collective object is related with the fact that the emergence of the collective objects is what makes the bee population to survive, but on the other hand, the very appearance of the objects is related with the properties of the individuals. So we have a kind of situation in which you might suspect, if you just look at the little movies, that these islands are teleological. They are trying to move in a place where it's good for them. But this is, in a sense, only an illusion of other, because we attribute significance to the collective objects. The real laws of nature, which we invented for the apes and the bees, they are causal. So this these explanations, which I try to make them intuitive, they are backed up by very strong theorems, which are essentially saying that, for instance, in 2 dimensions, no matter how large is the death rate, no matter how small is the density of the A's, no matter how small is the reproduction rate of A-B pairs, the bee population in 1 and 2 dimensions, if the lattice is 1 or 2, it always grows. This is a very unexpected and strong result. And here is again a simulation in which the factor, the alpha A lambda minus mu is negative, and you would expect that the entire system goes to 0, which it happens for most of the locations. You get this red background, which is 0. But you have these mountains, and actually the color scale is logarithmic. So these mountains are orders of magnitude higher than the smaller background. And you can compare this with the actual data of the number of enterprises per capita in Poland after liberalization. So you see that initially it is a relatively uniform distribution. You'll see that immediately, this is in the year of liberalization, you'll see that immediately after the liberalization, something very similar with this will happen. Very large regions will become red, which means that the number of enterprises went down. They were kept artificially alive by the communist planners. And however, some other places which are not high at all, they will become very, very developed by orders of magnitude, because for reasons which I will explain later, but which you understand. This is the normal behavior of an A-B model. So this is a movie. You see the large regions of red, but also very high peaks, very pronounced peaks of production. Because, as I said, this is the number of enterprises per capita. Understood? So in terms of absolute number of enterprises, it's even more, because these places are actually the places where the main cities are, where the university cities are. So not only the per capita is larger, but the the density of population is much larger there. So as I said, the situation was that if you looked at the first years after liberalization and you looked at the economy, then it was going down, and you would expect that it will continue to go down, especially if you assume that this kind of logistic model. However, if you look at microscopically, then what you see is that there are these darker regions which have, in fact, very high growth rate. They just started low, and they are very small. And because of this, they are not showing here and not showing here when I make the entire sum over entire country, Poland. But when in the next year, because they are going up so fast, then in fact they become the Polish economy. All the others are essentially negligible. So it's going up the next year. Not only that it's going up, but you say, okay, so you have an A-B model, but who are the A's? The B's, it's clear. It's, let's say, the number of enterprises in this case, which is somewhat proportional maybe with the GDP, maybe proportional to the wealth. But what are the A's? Well, this map is the map of education years per capita. The regions are completely corresponding to one another. And in fact, so the A's are essentially the education. You have a situation very flattering for a place like this, a university, in which the growth of a country, if you let it free, like in a capitalist economy, not as it was until that moment in which there was a planned economy, top-down planned economy, you have that what makes this economy taking off is the education. And so now pay attention, because I'm going to show 3 maps which are making this point in such a strong way that in a sense you can miss it. You see there are 3 maps here, 3 maps. This, this, and this. Now this and this are almost indistinguishable, so you have to pay attention when I'm showing them. The first map is the number of enterprises 5 years after liberalization. You see that there are very pronounced peaks in very well-defined places, and the rest of the places are pretty much not developed. Now the next thing, it's something very different. Remember, that thing was the number of enterprises per capita in each of these little regions 5 years after liberalization. This is the number of years per capita of education 1 year before the liberalization. And it is almost identical. I'm jumping again between them. So, on the other hand, if you look at the enterprises per capita in the year of liberalization, contemporary with this map of education, but just the enterprises per capita at the year of liberalization, that places which are so outstanding in terms of 5 years after liberalization industry and education, they are not even seen there. So this is, of course, a very a posteriori, very humiliating thing for a communist regime, because it shows they did have they did provide the education for a very efficient economy to take place, but they just weren't able to take advantage of it. So this this is a more quantitative thing. It's the correlation over the years between the education and the number of enterprises per capita, and you see that it's much larger than, let's say, the population size or things like that. And especially at the beginning. So after the... So now I'm going to... I will not have time to develop all the predictions which the system, which this model is giving, and confront them further with the empirical data. But I will start with it, and in the process, I will also give you a little bit more intuitive feeling of how comes that even though in average I don't have enough A's, so to speak, as to ensure the bee population grows, it's still the bee population still grows. Okay. So now I'm going to give an intuitive thing which doesn't have any formulas in it. It's just what this thing is the following. I have a lattice. In place of a two-dimensional lattice, I take a one-dimensional lattice. A one-dimensional lattice with 14 sides. Okay? And I have a density of A which is very small, 1/14. What does it mean, 1/14? Of course, if I would insist to spread the A uniformly, it will be something like this. But if A's are discrete, it means that I have in one of the places I have an A, and in all the other places I don't have any A. And these blue things are the level of bees. I suppose that there are very many bees, so that I don't have to worry about the discreteness of the bees in this particular explanation. So immediately after I start the system initially with a completely uniform distribution of the bees. So the blue line is here initially, it was a continuation of this. And I choose the parameters lambda and the average of A and mu such that in fact there will be this decreasing exponential. This would be the continuum limit prediction. Okay? And then the question is, does the discrete system behave like this? Well, at the beginning it does. Because you see, all these guys were going down. This was when going up, but it's only 1/14, and because of this, the first point and also the third one are actually not so bad. They are going. They are going down. But as I continue, you see that the place where A is growing, while all the other guys after that are going down, but they are going down. This is a logarithmic scale. A is already larger than 10, so all the others together are not as important as the place where A is. So the only thing which matters when I'm now making the sum of the bee population in the system, it's only the growth of A, and because of this, the discrete system is very much differently behaving than the naive system in which A would have been spread uniformly across all the sides. Now, of course, you can say, yes, of course, this is because A is not moving, it's sitting there. That's not a big deal. But what happens if A moves? And indeed, if A moves, at the beginning, all these guys which were in the old places of A are going now down. And since they were dominating, the entire bee population, if you want the economy, is going down. Until when? Until the new place where A is, it becomes dominant. You see, it's already here it became dominant. Here it's about 50, while all the others are below 1 because it's a logarithmic scale. So you have this kind of situation in which it is true that each time that A is going, it's moving, you have some temporary recession, but all in all, you have this kind of process in which you have this kind of what we call crossing exponentials. Why is it crossing exponentials? Because each time that one goes from one place to another, the old place is going down exponentially, and the new place is going up exponentially. So this is why I was insisting at the beginning of the lecture to understand just this little point, that you have, if at a certain place you have a lambda A, which is exceeding mu, then you get increasing exponential, and if in the other places you have lambda mu, which is lambda a, which is less than mu, then you have decreasing exponential. This is the only important thing. Each time there is a motion in the A, even if the system is much more complicated than with one single A, you have this kind of situation. A cusp, which is related with this shock, and this curve, which is essentially the combination of two exponentials. And I don't have much time to discuss this here. This is the graphs obtained by that previous simulation. This is the value at the site 4. And this is what happened as long as A was on the site 4. Then what happened after A jumped to site 5. And this is what happened when it returned to site 4. And on the other hand, this is what happened with all the other sites. Sites 1, 2, 3, 4, 5. I'm sorry, 1, 2, 3, 5, 6 until 14. It was going down as long as this was, the A was at the site 4. But when it jumped at 5, then they went up, especially because of the 5. And they went down again. So this, and then the sum is this kind of cusps, which are separated in between. You have just two exponentials summed one with the other. This is a logarithmic scale. So these are essentially two exponentials, and this is explained. The sum of them is this line. Okay? Now, why do I want you to remember that? Because now, with the time which I have, all I will do is to go to a graph, which is the real economy of Britain for about I think between 1990 and 2008. And it's exactly, you see, that each time there was a recession. There was one in 1990, mainly related with the first Gulf War and maybe with real estate. Then there was another one to real estate in 95. Then it was the dot-com bubble. Then there was another small crisis in 2004, and then the big one in 2008. So you have all these discontinuities related with, so to speak, the jump of the A's, the change in the environment in which the B's are moving. And in between, these lines are just fit by just two exponentials. So you have almost 20 years of an economy fitted by a very small amount of parameters, because it's not just some parametrization. It's just understanding that, in fact, the economy is behaving like this kind of A-B model, in which the A's are the conditions which the economy is behaving, and B's are essentially related with the GDP or the number of. The same thing, it can be applied to other countries. You can even use it in order to predict the behavior of the economy. Of course, you cannot predict the discontinuities. These are sometimes endogenous, but sometimes they are due to external causes which you cannot predict from inside the system. And I will finish with this very relatively impressive collection of data, in which after we took countries after there was shock in their economy, either a war or a liberalization or something like that. And this continuous line are always just two exponentials, nothing else. And as you see, they are fitting very well. And sometimes you even get this cusp, which I was speaking about, because there was, in those particular cases, we know what happened. In these three countries, there was immediately after the liberalization, there was some other either changes in the government or economic reforms or some kind of crisis. And here I will finish with somewhat funny way of putting this understanding. As I said, it's only one of the many understandings we got from this theoretical model about the real economy. In general, you might have a politician asking, what happens if I make a reform? And then a typical answer would be, well, it depends. Tell me what reform you want to do. I tell you what are going to be the results. But this model says, well, if it is a real reform, if it is really changing what is the dominant component of the economy, first things will look like they are going down because the bulk of the economy, is which was dominating until now, is going down, and something new, which presumably would be much better, but right now it's too small. Even if it has a very high growth rate, it will take some time until it shows in the general picture, will go up. So you would predict that, in fact, first it will go down exponentially, and it will then recover exponentially. And this, of course, brings you to the idea, okay, but maybe I can make this crisis of going down, make it less severe by having some transfer from the growing part of the economy to the one which is collapsing. Then you can do that, but then you prolong the transition period, in the best case. And in the worst case, you might have a situation like in the communist regimes, in which they were taking so much from the places where growth could take place and throwing it in places where growth didn't happen, that in fact the economy was going worse and worse. So I think that this is the right place to stop.